I am going to be getting through this as quickly as possible to leave time for questions. My name's Tom. I work for Habito. You can find me in various places. I'll put it up again at the end. So who cares about GHC 8.6? And the answer is I do. I really care. There's loads of fun stuff. And I'm not going to have time to go through it all, so I'm going to focus on the 5 extensions that I think are actually, quite exciting for reasons we're about to see. So, plowing on. Numeric underscores. Let's say you have this integer in your code. It's really big and difficult to read, and now you can put underscores in it. So now it's not really big and difficult to read. This is a plus. I struggled to find something interesting, except that the lexer doesn't care how many you have, so now you can write really wide integers as well. Perfect. Moving on, deriving via. I really hoped that Andres would just do this bit for me earlier, but unfortunately I do have a different example. This is a class I wrote a few weeks ago. It's not very interesting. It takes some raw user input and tries to validate it. And you can do some cool stuff with deriving via that maybe isn't immediately obvious. If I define this new type around a string that is indexed by some rules using some magical data kinds, and define some validation rules here, I can then write a class that loops over a list of type-level validation rules and applies each one to some input. And then using this apply type class, I can pull the nat out of the type and use it here to do some actual validation. So too short, too long. Why is this interesting? Because now I can write an implementation for string validator, and when I write a new type around a string, I can just derive its validation via this string validator. Super exciting. And of course, no matter how many new types I have, I can derive different sets of validation. It's amazingly cool. The one thing I did want to point out, if you do end up experimenting, if you add something to this class that has an ambiguous type, in this case A, there's currently a problem with actually it's GND, not deriving via, which doesn't let you derive this. Luckily, Ryan's already fixed it, as he has with everything else. So this will be out with 8.8, I think. Until then, there's a dirty trick you can play, which says just tag the ambiguous type with the actual type, and then everything works. And you can go back to it, and it's fine. Deriving via in 3 slides. Star is type, so probably not too interesting. You start with your industry Haskell code base, and the first thing you do is say, functor is a name that no one understands, I'm going to write a better one. And it ends up looking like this. And what star is type does, because it's on by default, is let you write this. And if you turn it off, you get in trouble here, because star is an operator, obviously. Like everything else in Haskell, like the multiply sign, star is an operator. This doesn't make sense. That is all no star is type does, is say this no longer means type, this doesn't mean anything. Luckily, you can now write type by importing it, which is useful because types are fairly important. But more excitingly, because no one needs types in the real world, you can now use star for what it was meant to be, which is type-level multiplication, obviously. So here's a type family. If you don't know type families, I think Stephanie talked briefly about them. It's just a function that multiplies numbers. But now you can use it for its proper purpose. A less obvious consequence of star as type is we can't currently write this and feel good about ourselves when validation is applicative. Also, Haskell might have a slight difference between the applicative and the monad instance that doesn't quite lawfully line up. No star as type actually fixes this in a really unintuitive way. Skeptics. If you turn on a bunch of extensions, including undecidable superclasses, you can write this. Still, can you tell what it is yet? What this means is you can now say terms and conditions apply when you write your instances that aren't quite legal, and thus this becomes self-documenting. You're welcome. No star is type. Quantified constraints is a really cool one. This is a list written as a GADT, and we can write a show instance for list if A is showable. The problem with lists is it has this really annoying constraint that everything has to be the same type. And I don't actually want that. I want to say I have a list of stuff that I can interact with in a particular way. So what I end up writing on day 2 of learning Haskell is a constrained list, indexed by some constraint constructor, if this all looks odd to you, the only interesting thing is this, which says rather than having a type of things in the list, I have a constraint that applies to everything in the list. And now I can write show for the list if that constraint is show. Easy, except day 3 of Haskell, you write this type family to have as many as you like crammed in there, and now you say everything in this list is satisfying all of these things. So it's a show, it's an EQ, it's an ORD, it's num, it's a JSON. You're in trouble because your show instance wanted show there, and now it doesn't say show. So what we want is a way to say this constraint implies show. And luckily, with quantified constraints, you can say this constraint implies show, which is exactly what you want. And now this works, except it doesn't. You get another fun bug that Simon very kindly explained to me. So the problem is, as I've drawn very delicately here, there are 2 instances for show when GHC tries to write the rest of the show type class for us. There's this one, because X can be unified with constrained show, and this one, which is the one you actually want. And the problem is GHC says that's the one I want to use. Oh dear, it's probably fine. And thus, it's not fine. Oh no. Wait, I bet that goes in there. It's back. So, it's back. Everything's okay. So GHC picks the one I don't want, which is super annoying, and Simon assures me, actually, you can go and look at it. He writes this lovely message that says at the end, feel free to propose something different, which I'm far too scared to do, so we're just going to live with it. And the way you actually get around this is you introduce a new type, which can use deriving strategies to just borrow the show from the inner thing, and now this instance head doesn't match constrained list, and everything's just fine. You have to write transparent there, but otherwise, problem solved, and now you can have what you want. So the last one of the 5 to talk about is block arguments. I wrote pure script before I wrote Haskell. This is hideous. And with block arguments, we can do that. And that is literally all it does. And it's beautiful. It turns blocks like case and do into arguments. It's a brilliant name, really is. So it was difficult to think of something better to say about this, because it's not that interesting. But in well, funny you said that. So I went looking for something. And in pure script, we have hating algebra and Boolean algebra, which are bad names for things that are bool-ish. So bools are bool-ish because they do all these things. But also functions are bool-ish if you unify the outputs. So I can and f and g if the output can be anded, and then I get this. Why would I want to do this? Because now I can write this combinator. And coming back to your point, you'll notice the lack of monad catch means there is no try. Any questions?
One question. Why?
So the question was why. The answer was which bit? Oh, I don't know. Try to think of a more interesting example. The thing is, 2 out of 5 of these, there are useful things to say in a slideshow. 3 out of 5 of them, there are fantastic documentation, and I had to fill the other 8 minutes of my talk. So.
Okay, thank you.
Well, perfect.